Write down the references in the first two lectures that I'm following, but these three are the main references I'm following. All of them are available online without subscription. And I want to mention that this paper, which originated this theory of diagrams or coefficient systems in the model setting, is actually very readable, even if you have not seen this model theory before. So please, you can read this paper just from the beginning. It is self-contained. Okay, so so where were we last time? So in the first two talks, I defined the formalism of diagrams and wrote down the main theorem, which is in this paper by Pasculas, which gives us a way to construct or show the existence of supersingular representations from something called basic diagrams. And I also gave you two examples at the end. So the examples of basic diagrams. So I will continue from here again. So I recall that we saw these two examples of reducible basic diagrams, and this was when my residue field was FP. In the first example, this D0 was the sum of two weights of the form sigma and sigma s, and in the second example, my D0 was a non-split extension between sigma and sigma s. So I will write now non-split extension by this kind of picture. So here this means that this is a non-split extension between these two weights with so-called sigma and so-called sigma s. And E1 was nothing but I1 invariance of D0 on both sides. And the action of T was given by some scalar from HP bar star in both situations. I'm just recalling this thing from the last talk. And in the today's tutorial, you will show that first of all, these are irreducible diagrams, and as I vary lambda, so I write it in the middle. So lambda is some scalar in FP bar, non-zero. As one varies lambda, the diagrams that you get in example 1 are all isomorphic, but they are not isomorphic in this situation. So this is also part of today's tutorial. And third example. So now let me take Q equal to P square, and D0 is now going to look like direct sum of 4 non-split extensions. Okay. So now I want to sort of give an example in this situation, Q equal to P square, which captures some properties of both these diagrams. So let me say what I mean by that. So let me first write down what is D0. So D0 is going to be direct sum of 4 extensions. So non-split extension. So it has a circle consisting of 4 weights. So let's call them sigma 1, sigma 2, sigma 3, sigma 4, and then I am going to take a non-split extension of sigma 2 by sigma 1 s, sigma 3 by sigma 2 s, sigma 4 by sigma 3 s, and sigma 1 by sigma 4 s. Okay. So D0 has this kind of shape, but one may ask, can you find such a weights, right? Sigma 1, sigma 2, sigma 3, sigma 4, which admit non-split extensions like this. So it is true. So this is the direct sum of 4 extensions. And what are these weights? So I will just write down explicitly. So recall that any weight of G into F cube, the notation was f tuples of integers between 0 and p minus 1 and extra integer m which gives you determinant character. So r bar and m. So here we are in the q equal to p square situation. So we have 2 tuple to begin with. So I start with r0, r1, and usually one also has determinant power character, but one can just take it to be trivial. So I won't write it down here. And let me finish writing these entries of these weights. So explicitly. So these are the weights which admit extensions of this type, and one can take the direct sum of all these non-split extensions. And if you now again take D1 to be I1 invariant, so D0, which is same as U FP square invariance of D0, all these weights will contribute to I1 invariant space. So this is basically direct sum of chi I plus chi IS. I runs from 1 to 4.
If the diamond weights attached to a particular kind of robot.
These are this is not D0 of a.
The base.
You mean
the base weights? Sigma 1, sigma 2.
Yeah, the base weights are diamond weights, but D0 is not the diamond diagram. D0 of a diamond diagram. The D0 of a diamond diagram has a shape like this kind of, and that's why the name is diamond diagram. And here we are only considering this kind of.
Diamond diagram is a spread diagram.
I also used to think that, but Roy Pascuna said that it is because of the shape of the D0. Rule of? Yeah, so in the definition of a diagram, you want to have a K0 representation D0 and K1 representation D1. K1 representation was generated by K1 as a group is Ivahori and this particular matrix 1 anti-diagonal 1 pi. That was this T. Okay, so if you want to give a K1 action on D1, there is already a Ivahori action which is coming from K0 action on D0. You just want to give the T action, and this is the definition of a T action. I did not want to again recall the notation, otherwise I won't be able to finish. Okay, so here.
I mean, it might help to remind that again and again, but it's not some random ways.
Yeah, I did.
Some canonical way, I mean, for the audience,
Yes.
not to you, people, that I mean, it's a canonical way from a multi-guide organization.
Yes, that is right, but one can actually come up with these kind of formulae only by studying the GA to FQ representation theory. But there is a connection of these bits to the Morphy-Galois representation, which I am coming to in the end of my talk.
Sir,
Right. Yes.
drawn those diagrams, how you age is looking like, vertices of this dimension. Can you draw
Yeah,
this?
so, okay, what does this mean, right? Yeah, so if you have, so do you understand this picture? It's just a non-split extension between two weights. Suppose now if I have a diagram, a picture like this, I will say picture instead of diagram, like so. Maybe not, something like this. What does this picture mean? First of all, it means that again, it means that sigma is the socle of this representation. If I go modulo sigma, I again get some representation, and this tau 1 and tau 2 are going to be socle of that representation modulo sigma. So this has a sort of two-step filtration. This is only one step. So if I write V for this representation, I have socle of V equal to sigma. Socle of V modulo sigma is tau 1 direction tau 2, and then I can again do socle of V mod sigma mod is tau 1 direction tau 2. This is this top weight sigma prime. This is the meaning of this picture. And these edges denote that there exists a non-split extension between each weight. So there is a quotient of V, which is a non-split extension between tau 1 and sigma prime, tau 2 and sigma prime, sigma and tau 2 and sigma prime. So that's sort of clear. Okay. Yeah. Yeah.
That circle should be outside the quotient.
Circle should be outside the quotient.
It's not circle of V mod.
Second line, second.
It's not.
Yeah. Right. I wrote it correctly.
Yeah, and in the third line also it is circle of V mod sigma quotiented by tau 1.
Circle of V mod
Third line,
sigma.
third line.
Yeah. So I'll clear that. Okay, so in this setup, I want to now define what the T action is, and this is again similar to the example 1 and 2. So let me write it here, that we just take T chi I to be E chi I S, or I equal to 1, 2, 3, and we will E chi 4. On E chi 4, I take T divided by lambda. So you can as well multiply by some scalars here also, but they all give rise to isomorphic to this particular diagram. So again, lambda here is implies. So okay, what is the point of this introducing this diagram? So let me. This situation, why I said this kind of captures both the things happening in example 1 and 2. First of all, you can see that okay, so these again consist of some extensions between weights, although they are not extension of sigma by same sigma s, but there is, you can see some kind of this phenomenon happening here, and as well as why this is also captures properties of this D0. If I take U invariants, a priori one might expect that the co-focal weights need not contribute to U invariants, all of them. But in this situation, the space of U invariants is coming from all the weights. So each weight U invariants is one dimensional, and the space of U invariants is here is 8 dimensional, which is coming from all the weights. So, so let me again write. So as lambda varies in example 3, again these are similar to example 2, non-isomorphic, irreducible, basic items. And so, and hence gives maybe Q. These are irreducible diagrams, and hence they give rise to a family non-isomorphic, irreducible, admissible, super singular representations of GI to F, where note that our residue degree of F is p square. Okay, so in this situation. So yeah, and okay, one more important maybe point that with trivial action of the uniform function. Because in the diagram itself, the definition of a basic diagram, this element acts trivially on D0. So the immediate consequence of this thing is that if you take the compact induction in this situation of any of the sigma I there, okay, and go modulo the image of T, this has, yeah, so this is not of finite length. The fact which I mentioned in the beginning of my first lecture. Again, important that Q is equal to P square. For when F is QP, we know that in fact this is irreducible, but as soon as the residue field is Fp square, just degree 2 extension, not trivial extension of Fp, this kind of object has infinite length. Okay, so there are a few remarks. One may ask then why this kind of construction doesn't work when Q equal to P. But the point is, you don't have these kind of objects when Q equal to P. You can only get this kind of object in the non-state extension. When you go from Gn to Fp to Gn to Fp square, the representation theory becomes more rich, and you get all kind of interesting extensions between weights. But for Gn to Fp, you don't have this kind of object. So maybe one remark which I should have mentioned earlier. So this is again a general fact that given sigma and tau weights, alright, so this remark is basically what I said right now already, but okay, let me write it down again. So if you look at the extension group between two weights, as a vector space it is one dimensional. Takes as a GI to FQ representations. So there is a unique non-split extension between any two weights. This is true for given J, F. when Q is not necessarily P, and it can be precisely described when they have a. I don't want to write down the formula, but let me just say that described in terms of sigma and tau. When when it is 0 or 1, it meaning this extension group between sigma and tau, and then the remark says that when Q is equal to P, okay, let me just extensions like in example 3 do not exist other than the principal series. Okay, so this is just I was saying without giving any details why this kind of thing doesn't exist for QB.
The sigma is on this board.
Yeah.
The same that the sigma is on that board.
Sigma is one of these three.
Sigma is board.
Yeah. So
For some I or all I?
all are.
What is the argument again?
Hmm?
What is the argument again?
Yeah, so any representation which is coming from this diagram occurs as a quotient of induction of any induction of kz to g sigma I mod t. I can be all of them. Is that clear?
Sigma is in the socket, so that
Yeah.
is reciprocal to have such a map.
Yes. And this is we usually the Parthian necessity this is t minus lambda, but since we can see that clearly that it is super singular, you can use the dimensional criteria which I mentioned in the lecture too, that lambda has to be 0. Conclude that it is super singular. So it's a quotient of induction modulo E. So here
You might have to say as you weight is, you get all weights, right? Weight
Yeah.
to R0 and R1. Right?
right. Yeah. So there should be one has to be maybe take into account generic weights, so maybe the condition that R is strictly between R0 and R1 both are strictly between 0 and t minus 1. Maybe one should have this condition to have multiplicity, and there are some details which I did not mention, like for example, if you have two different basic reducible diagrams, why the representations are again different, known as what that uses this, that it should be multiplicity.
So in example 3,
Yeah.
so when you write a vertical line,
Yes.
it means a non-split extension, right?
Yes.
Okay.
So
Usually there is no tension between sigma 1 and sigma 1 S, right? Isn't that part
there
of
is
the-
no extension for when Q is not P between sigma and sigma S.
If you wrote that few times, did you mean some?
Those indices were different.
It was between sigma 2 and sigma 1 is sigma 3 and
Okay, great.
okay. So examples of diagrams in 3, they can be generalized to higher Q as well. I gave Q equal to P square example, and I wrote a short note on this actually. But before maybe coming to that, I want to spend some time talking about injective envelopes. So this is interview. Injective envelopes. So if you again check the theorem of Breuer-Pascunas, theorem 2, there was this capital omega, okay, and it was sort of, I didn't say what it was, I just said there exists some smooth G representation. So I want to say what that is in very short, and for that I need to talk about injective envelopes. So let me now, I have two categories, GI2FQ. So this is the category of representations of GI2FQ on XP bar spaces. And I'm also going to consider another category. So for this section I am following Pascunas paper. So let gamma be a profinite loop and assume that gamma contains a propy subgroup which is open and normal. Open, normal, propy subgroup. So example typically is the K maximal compact GI2O or GI2ZP and then I write ray gamma for the category of smooth gamma representations. So on again, FP bar vector. So what is an injective object? So my C is going to be either GI2FQ or gap. So let us recall what is an injective object. So recall that I in C. Injective object is something which, so okay, write it down. So is injective, is called injective if the functor from morphisms in C to I, this functor is exact. So what does this mean? So that means IP given tau 1, tau 2 in C representations. such that tau 1 is a sub-representation of tau 2 and a map to I. This map can be lifted to a map from tau to I. So, given this, in C, there exists f from tau to I such that this diagram comes. Okay. This is just okay. So if C is semi-simple, which is not, every object, let me say just as a fact, every object is injective in a semi-simple category. This should be clear because semi-simple category means that every object you can write as a direct sum of simple objects, and then basically if your object is a sum of two objects, then you home of that object to I can also be written as a sum of home. So that is again, that gives you exactness. Right, and so when the category is not semi-simple, one tries to hunt for injective objects, and given every simple object, there is a natural injective object associated to it. So that is what I am writing. So irreducible objects or simple objects in C. So this is a very brief introduction to injective envelopes. Okay, without any proofs. But I will give proof of one important theorem at least. So irreducible objects in C, which is not semi-simple because we are in characteristic P, they are in one-to-one bijection with injective indecomposable objects. And suppose I have a sigma which is simple in C, I call the corresponding injective indecomposable object its injective envelope and denoted by inj sigma. So formal definition here. So here I just said that irreducible objects are associated with injective indecomposable objects in a unique way, and they are in fact the injective envelopes. But what is the formal definition of an injective envelope? So let tau be any object in C. So some representation, an injective envelope. Okay, there are maybe two equivalent definitions. So injective envelope of tau. So this is one of those. So it's an injective object first of all. Okay, containing. So it's the name has a word envelope, so it should contain that tau. Injective object containing tau. Such that if I take any other object, so injective object, so let me call this inj tau. such that any non-zero sub-object of this injective object which contains tau, okay, sub-object of inch tau intersects with tau non-trivial. So what is the injective envelope of a tau? It's an injective object in C containing tau such that if you take any other non-zero object, sub-object of this injective tau, intersection with tau should be non-zero. So equivalent, there is a, I said there are two equivalent definitions, so maybe equivalently, I'm not going to prove this characters, another equivalence. Equivalently, inch tau is an injective object with the same socle as tau. Such that socle of tau is same as socle of injective envelope. These are equivalent definitions. And the theorem which is there in the Pascular's paper I mentioned, 4. In fact, maybe if you paid attention to Dotto's talk, this theorem 4 holds in much more generality. So what is the theorem? That injective envelopes exist in category C. So let me give some facts which are easy to prove. That yes. C was either representations of GI to FQ or representations of GI, smooth representations of GI to ZP. So, given any representation, GI to FQ representation over FP bar vector space, there exists an injective object, injective GI to FQ representation with the same socle as that of the given representation. And the same thing is true for in the smooth representation category. Given any smooth representation of a GI to ZP, there exists an injective object in that category. That means it is also smooth representation, and they share the same socle. That is okay. Instead of this is a fact. Actually, this is also one small lemma in Pascular's paper. So. Let me just write this. So recall that this gamma was a profinite group which contains Propi subgroup. Okay. So if I now take some sigma irreducible object in the representation category of gamma. Okay. I can look at its injective gamma envelope, and I can take the P invariants where P was the Propi subgroup. Okay, I can take its P invariants. This is actually same as the injective envelope of sigma in the category of gamma mod P representations. Okay, so now I want to prove one very interesting theorem which holds only in the characteristic P situation, not over complex numbers. So theorem 5. Let's say G is a locally profinite group. So you can just will assume that G is Gi to F. And suppose G has a open property subgroup P. So, for example, you can take I1 or K1. Then a smooth G representation is admissible if and only representation pi, if and only the p invariance of pi is finite dimensional. So what this theorem is saying that in this over characteristic P, suppose my group has a propy subgroup P, it is enough to look at for admissibility questions, it is enough to consider invariants under any propy subgroup and show that it is finite dimensional. Admissibility definition, if you recall, it says that for all compact open subgroups, the invariants should be finite dimensional, but this theorem says that it is enough to prove this for some propy subgroup. For Gi, so the corollary of this is the following. So for Gi to F, pi admissible if and only k focal of pi is finite dimensional. So I did use this corollary in proving theorem in the proof of corollary of theorem 2, and I said that we will come to this later in the course.
Don't we need P to be compact?
P to be compact, you mean propy by
Achha, okay,
definition.
propy, yeah.
Propy.
Yeah.
So the proof uses a very nice argument involving injective envelopes. So let's look at it. Okay, yeah. So why the corollary follows, you may think that, so k focal of pi always sits inside k1 invariants of pi, and k1 is a propy group. So if I know that, so k focal of pi is finite dimensional, that's also a good question. That doesn't directly imply that k focal of k1 invariance of pi is finite dimensional. Yeah, good point actually, Harish. So this is the first step maybe, and one also has the following, which k focal of pi is same as k focal of k1 invariance of pi, and if this is finite dimensional, then k1 invariance of pi must be finite dimensional. So here I am is finite dimensional. It's like okay, I think okay, sorry, I should say here, I should write down one more fact, that if focal of tau is finite dimensional, implies that tau itself is finite dimensional. Yeah, so thanks. But I am just stating down some facts, and but maybe at least from these things, is it clear why it follows? have used the admissibility to show this. I am saying this is equivalent to saying that K circle of pi is finite dimension. Yes. Because admissibility means that under any compact open subgroup, the invariants are finite dimensional and K circle is sitting inside invariants. So this way is sort of clear, but the reverse direction again uses some facts. Right, and okay. So the proof here.
Okay, so
Yeah.
when you're using the theorem,
Ah.
you show that this given index of pi is finite dimensional.
Yeah.
So using the theorem, we get pi z.
Yeah. This is kind of this statement here, like in particular I should say. It's not in particular. It's a corollary of the theorem. Theorem it's here. Okay, so proof I will write down on the board. Again, one more point here, aside maybe. So you know that if you have a complex representation of GI to FQ, if you look at the group algebra, this decomposes into irreducibles, and each irreducible has multiplicity equal to its dimension. Okay, this I suppose everyone knows from representation theory. Sigma is irreducible. So the analog of this theorem in the multi setting is the following. If I take the group algebra over FP bar, it also decomposes into now not irreducible objects, but all injective and decomposable objects. So dimension of sigma, but instead of sigma I replace it by injective envelope of sigma. Again sigma irreducible. And from this description you can easily see that if what is the injective envelope of a let's say P group, finitely P group. So if I have, my notation is UFQ, this will be sum over dimension sigma, injective sigma, the irreducible representations of now UFQ, but you know that there is, for a P group, there is only one irreducible representation in characteristic P. So this sum is basically just one representation, and that representation is a trivial character. So the dimension of is 1. So injective envelope of the trivial representation of UFQ is the group algebra. Injective of trivial character of UFQ, upper triangular unipotent, which is a P group finite P. Is this? Okay, so let me
The previous proof, sorry, I'm only partly paying attention.
Yeah, yeah.
Previous proof, did you give a complete proof or not?
No, I haven't started the proof.
Ah, yeah,
The proof of this theorem. So we want to show the if P invariants of pi is finite dimensional, then the representation is admissible. So this is clear by definition of admissibility. So the reverse direction. So suppose dimension pi P bar is finite enough to prove that dimension fp pi p prime is finite, where what is p prime, where p prime is open subgroup of P. If this first reduction step is clear, we want to show that if P invariants are finite dimensional, then representation is admissible. That means for all compact open subgroups, the invariants should be finite dimensional. But suppose if I have some compact open subgroup K, I can intersect that with this given P. I will get some compact open inside P, right? I can if I show that this intersection of K with P is finite dimensional, that will give me that K invariance of pi is also finite dimensional. Okay, so I can replace any compact open with its intersection with P, and I can as well make this intersection normal. This is again easy by profiling groups. You can take intersection over all G.
Boundaries. I'll just stare at that. Yeah.
Okay, so this is basically this kind of reduction. So, okay, so now let's consider the look at this space here, P invariance of pi. Okay, I have this is sitting inside pi, of course. Okay, where I now look at pi as a P representation. So let me write it as a restriction to P. Okay. Now as a P representation, what is this? This is a trivial representation. It's a P invariance of pi. So I can write this as a, and this is also finite dimensional. So this is nothing but dimension of pi p times the trivial character. We have that dimension of pi p is trivial. Huh? Why this is equal? Yeah, as a P representation. So I am considering this in the rate in this category. What is this as a P representation? What is this object?
Yeah, so it will be sum of trivial.
This, yeah, sum of trivial and finite trivial. Okay, so now for this trivial P representation, I have injective envelope in this category. So injective P of trivial. Okay, for this just one. Okay, this is the injective envelope, and I can also take the direct sum of these injective envelopes this many times. Okay, so dimension pi p of this injective. Then this thing here is injective envelope of this thing here. Okay, right? So so this thing is injective envelope of this thing. So clearly this is sitting inside this. So I have this. So everything here is in this category. In the smooth representations of P group. P is a pro P group. Now this is injective object in this category because this is an injective envelope. So by the definition of injectivity, we know that there exists a map which makes this diagram commutes. Let's call it phi. Okay, and so this is basically same as injective P envelope of this trivial representation. Okay, so my first claim is that psi is injective. It is not clear immediately from this diagram if this is injective and this is injective. Usually it is not true that this is injective again. So and this. So why psi is injective? So let's look at the kernel of psi. And so kernel of psi is some sub object here in pi restriction to p, and I take its intersection with this p invariance. Okay, so this is same as kernel of psi p invariance. I haven't done anything here. Let's take some vector v here. What can you say about v? So v is here, which is mapping to kernel of this map, and this composition is same as this arrow, and this is injective, so v has to be 0. So if I take some v here, implies v is 0. This means that p invariance of kernel of psi is 0. Okay, but we are this would imply that kernel of psi itself is 0. Why? Because in characteristic p is a pro-p group. If it was a non-zero representation, pro-p group would fix a non-zero vector. But we got that the invariance of this representation under pro-p group is 0. That means kernel of psi itself is 0. Okay. Yeah. So this implies that. So this is injective. That means if I look at my representation pi, its restriction to p is actually sub of this. Okay. So pi is sitting inside injective envelopes of real representation, p injective envelopes, dimension many times. Injective p of real. And I want to show that p prime invariants of pi are finite dimensional for any p prime which is open normal inside p. So I just take now p prime invariants on both sides. So I get p prime here, and this is just a sum of this object, this dimension many times. So this will be p prime. Okay. Now I am going to use the fact which I erased. So this thing here is equal to dimension of pi p, and this p prime invariance of this injective p envelope of trivial representation is nothing but injective p mod p prime envelope of p. Okay, and see p is a pro-p group. P mod p prime is going to be a finite p group. Injective envelope of a trivial character of a finite p group is nothing but the group algebra. So this is finite dimension. So in the end I am getting that this is nothing but dimension of pi p times fp bar group algebra of basically fp bar group algebra of p mod p.
Also p invariants outside, right? Also p invariants outside.
P invariants
So
outside.
that injective sub is from the previous one.
I did not get the question.
That's the previous one. So it's
Is that yeah? So this is finite by assumption. This is just finite group algebra. So this has dimension finite. So we have okay. So
Why is K intersection being bounded?
A intersection of this K is this thing. This is a subgroup of K. Sorry, what was the
Why is it
question?
non-trivial?
Non-trivial. These both are open subgroups. Intersection of two open subgroups is non-trivial.
you don't need that.
Okay, so now so this proof is in Pasterna's paper. And here this is true for any locally covariant group which admits of open tropism. So very strong statement. Okay, so now a word on proof of theorem. This is just very so theorem 2 was given a basic irreducible diagram. There exists a smooth G representation capital omega such that D sits inside constant diagram on omega and the circle of D0 is same as D circle. So what was the setup of theorem 2? I have 20 minutes, right? Up to 12:15.
Yeah, 12:15 plus 5 minutes.
So we have a basic diagram.
We also have a tutorial, so we have time.
Like this. I'm not going to recall. And this omega, which was a smooth G representation in the statement of theorem 2. If you, it's as a K representation, this is nothing but the injective envelope of D0.
But these notes have a much shorter proof of this, right?
Yes.
Yeah.
Which I can see, but it's for only J to Q.
Okay.
Yeah, it's the same kind of tutorial technique works.
So this is basically an index.
Okay, so maybe let me just write this down. So this omega was nothing but okay. So given a basic diagram D0, one can consider a injective envelope of D0, and one needs to make this into a G representation. So how does one do that? So I will just I'm not going to explain this, but maybe one line that one puts K0 and K1 actions on this each K0 which active the intersection, and this gives us smooth chair. Again, this I mentioned in the first lecture how one gets a smooth G representation from this kind of set.
Mihir,
Yes.
I think the last theorem is true even for any topological group. Last theorem, G.
Last theorem.
Yeah.
Sorry.
That is not only true for GL to QP. I think for any topological group it's true.
in hazing notes.
Yeah.
Okay. Yeah. Yeah. Okay. I did not check that.
Yeah.
And again by so then it is clear that Sokal requirement is satisfied there, that so K omega naught is nothing but so injective K envelope of D0 which is same as so let me write down few remarks here. So the process of constructing so the putting these actions on this injective K envelope of D0 is highly non-canonical. So there are several choices involved in this. So this is irreducible basic diagrams is this highly non-canonical. So although the construction H0, if you remember, H0 of diagram was functorial, constructing irreducible admissible representations out of that H0 is highly non-canonical. And the second bullet point, it is not true that all irreducible admissible representations of GI2F occur as quotients of H0 of irreducible basic diagrams. So what we have seen is that given the irreducible basic diagrams, there is a way to construct irreducible admissible quotients of H0 of that thing, but it is not true that all representations occur this way. But maybe here I want to mention one open question. In my opinion, these are the simplest super singulars for GI2F when it is not particularly. So open question is the following. We don't know the classification of irreducible basic diagrams when Q is not P. Or Q bigger than P, not. So actually this question is essentially just the GI2FQ representation theory. But still this is not known yet. And if you know all irreducible basic diagrams, you will get many super singular representations, and they will be in some sense the simplest super singular representations. Unfortunately, they are not important from number theory point of view, because those representations they won't occur in multi-local languages. But still, from a representation theoretic point of view, they will be in some sense simplest super singular. So maybe if someone is interested, one can try this, but this is hard. But it is just the GI2FQ representation theory. That is the point I want to make. Okay. Now I have 15 minutes remaining. If you start with some irreducible basic diagram, the irreducible admissible representations coming from H0 of that thing, they don't occur in number theory. Because if you remember those diamond diagrams, they are not irreducible, but they are indecomposable. So, diamond diagrams, so the representations which are important in number theory, they come from something called diamond diagrams, which I want to mention now. But those diagrams are not irreducible basic diagrams. They are basic diagrams, but they are not irreducible. So first one should look at irreducible objects, then indecomposable objects in the category of diagrams. But Breuer-Pascual were interested in application to multi-Langlands, so they constructed some indecomposable objects. Any things to say? So now this completes the interlude on injective envelopes. So and then coming back to examples, so there is a generalization. So I started looking at irreducible basic diagrams for Q equal to PQ, P power 4 and so on. And I want to maybe just mention this. So of basic diagrams. which was for q equal to p square to higher q. So let me just write it down. There exists a finite dimensional representation of GI to FQ of the following structure or shape of the shape. So in example 3, we had 4 extensions, right? And sigma I had a non-split extension with sigma I minus 1 is the similar kind of representation exists for any q. So of the following shape, so sigma 1. So now I have some kind of situation up to sigma 1 to sigma n, and similarly sigma 2 has extension with sigma 1 s dot dot dot. Sigma 3 will have a non-split extension with sigma 2s, sigma n will have non-split extension with sigma n minus 1s, and sigma 1 will have extension with sigma ns. If my f is 3, this kind of weights work. Let me just write it down maybe for your someone is interested. So now we have 3 tuples R0, R1, R2. I'm not writing the determinant character, but the entries look like this: R1 plus 1, P minus R2, R0 minus 1. With some determinant power, and here I have taken it. So okay, so that there exists such kind of objects for higher q, such that not only this, but if I take u invariants, then all the weights contribute to the u invariant space. So that means direct sum chi I plus chi I is I from 1 to n. So this was this is not difficult actually to say that there exists such kind of representations, but maybe one says down. And then as before, one can constructing basic irreducible diagrams out of these as before. What do we have? We obtain the same kind of result, that universal supersingulars. We obtain that compact induction is A to G sigma modulo image of E is not of finite length. But now this result is true for any f bigger than 1 is not of finite length. And I also want to mention here that these constructions also don't require my f to be p-adic field. It can be a local function field also. But again, number theorists are not interested. Local function fields is not of finite length for all q bigger than. So again, maybe q was p power f. And so this has a nice consequence. Corollary says is the following. Nice as in it's a negative consequence, which is the failure of multi-local Langlands, one-to-one multi-local Langlands. So for q bigger than p, there does not exist one-to-one correspondence between two-dimensional FP bar representations of one group of F and irreducible, admissible, supersingular representations of GI to F, which is compatible with the local classical theory, compatible with NCMW local classified theory. And why this is so? The following, so let me just one line through. So we want, suppose there exists a correspondence, we want at least that it should be compatible with local classified theory, meaning that if I look at the determinant character on the Galois side and central character on the GI2 side, they should match by the local classified theory map. But we know that if I fix the fixing the determinant of the Frobenius, there are only finitely many objects on the left side. The LHS is finite. If I fix determinant character, but RHS is infinite. So this is just a set theoretic. There is no control correspondence. Okay, I am not going to prove that. Yeah, I am not going to prove why there are only finitely many irreducible two-dimensional representations with the fixed central character on the Galois side. But at least you can see that the Frobenius corresponds to the uniformizer here. And in the definition of a basic diagram, I am taking uniformizer to act trivially. And and we know that constructing basic diagrams as before, meaning I can choose some lambda in FP bar star, and then these basic diagrams will be parameterized by that lambda. So I get infinite family of basic diagrams, infinite family of irreducible and disposable. So there is no such a correspondence even when over local function. This was already observed by for f equal to qp square. And if you paid attention to Karo's lectures, interestingly enough, there is a correspondence, again set theoretic one-to-one correspondence between Galois representations, and instead of representations of J2F, you replace this by simple supersingular Heka models. And some remark here now, using the above irreducible basic diagrams, above meaning these kind of structures, one can actually prove many interesting representation theoretic properties of this category. One can show for Q bigger than P, GI2 admits smooth irreducible representations which are not admissible. So this was first this kind of representations were constructed by Ley using other kind of diagrams, but together with Professor Ghateli and myself, we extended this result to any p-adic and local function field group using these kind of diagrams. So maybe people who are familiar with complex representation theory, they might be aware of the result that every smooth irreducible representation is automatically admissible over complex numbers. But here we are over FP bar, there exists some smooth irreducible representations which are not admissible. And recently, Daniel Lee also showed that there exists smooth irreducible representations which, so same thing, which do not admit central character. So again, these are all representation theoretic properties, characters over FP bar. Again, using diagrams of this kind of form. So in the maybe I can take 5 more minutes. Right. So in the last 5 minutes I want to explain. What is the importance of these kind of constructions in number theory.
One can show for Q greater than P.
Yes.
The GL2 admits smooth irreducible representations
Which do not.
which are not admissible.
Yeah.
That representation contains have a central character.
Yes, that do have some. Okay. So actually, the second result, which do not have good central character, implies that they cannot be admissible. So the second result is stronger in that sense. So the final 5 minutes will be application to the hypothetical multi-local language of Jammu. So now I am going to assume A is unramified over QP. Okay, I think I will skip most of the part here because it will take just half an hour. So again, theorem 2, if you of Pascunas, which was about existence of representations, but with the condition that the circle of D naught is same as the circle of the K circle of representation. And using that, maybe one can try to construct representations which might appear in hypothetical multi-local Langlands. So far you might have understood that for GL to QP there is a nice correspondence, but which fails when you replace when you go from QP to higher extensions. So let rho be So first let's consider F equal to QP. So let rho be a two-dimensional representation of the while loop of QP. So continuous irreducible representation with, again I am assuming this trivial determinant of rho of Lubelius. Then this rho has the following form. Again, this appeared in many lectures. So rho is actually isomorphic to induction from while loop of QP square to while loop of QP of fundamental character of level 2 omega 2 power r plus 1 for some r between again 0 and t minus 2. And let me actually, rho is of this form, and I will put bar because we are over 40 situation, and this is the integration that much. Okay, but I will take 5 more minutes again. And let's call such a induction rho bar r, and then mod p LLC for GL to QP maps rho bar r to the supersingular representation of the form this phi sim r 0, 1. Okay, the r in this range. Now one can, the restriction to inertia, this is nothing but the sum of two characters, omega 2 power r plus 1 direct sum omega 2 power p r plus 1. Okay, and on this side the case over here on this representation sim r 0 comma 1 is nothing but what is this sim r p bar square direct sum sim r p minus 1 minus r f p bar square increment power r. Okay, so here on this side you are getting two weights corresponding to r and p minus 1 minus r. If you just replace r by p minus 1 minus r in this thing, you will again get the same restriction. So this we can check that omega 2 p minus 1 minus r plus 1 plus omega 2 p times p minus 1 minus r plus 1, and then one has to take a twist here by a mod p cyclotomic character tensor with omega power r. This actually corresponds to this determinant twist here, determinant power r, and these two weights correspond to the change of variable from r to p minus 1 minus r. So this was the idea of change of variable kind of thing, r to p minus 1 minus r. Okay, so this was the story for f equal to qp. And what happens when f is unramified over qp? So for f over qp unramified, one can again consider the restriction of a wide group representation to the inertia, and considering all I will just write all possible ways of writing restriction. So there are here two ways of writing this restriction to inertia, right? All possible ways of writing the restriction of writing rho bar restricted to IF now. Breuil-Pascual attach. So here there are two ways of writing this restriction, and correspondingly we have got these two bits. So similarly, looking at all possible ways of writing rho restricted to IF, Breuil-Pascual attached a set of weights to rho bar. So W rho bar. So this is a set of irreducible representations of J to FQ and a family of diagrams. Again, these are basic diagrams, but very important that these are not irreducible. Basic diagrams, D rho comma R. So the such that what is the main point here, that if I take C, so for D0 of rho bar R, its case open is same as these weights. Okay, sigma inside. Oh, sorry. Take some sigma. Okay, now what is the point? There is a conjecture which was first made by Sayre and then Bazar, Diamond and Jarvis. That so if I start with some rho bar for now F over QP unramified, the corresponding supercuspidal representation, I mean, it should correspond to some supersingular or supercuspidal representation under hypothetical correspondence. Corresponding supercuspidal pi of rho should have the case occur given by G space. So pi rho as the K socle equal to direct sum of sigma inside W of rho bar. Okay. So now the last, maybe just one more line. VP's formalism of diagrams allows us to construct such representation, right? That was the theorem that we can control the socle. Formalism of diagrams construct such representation. So then one may ask, then we have a correspondence. We are starting with some irreducible Galois going with representation. We have a supercuspidal representation satisfying this Sayre-Bazard diamond Jarvis conjecture. But unfortunately, this is not a unique construct such representation, however infinitely. There is, then how do we single out representation that should occur in the correspondence? So there is a now there is a very much activity going on this area, and I maybe just want to mention some names that Emerton G. Zavi, then who Lee, Mora, Shrine, they all are, and finally also Tokyo. They are trying to single out the diagrams as well as representation using global methods. So maybe single out diagrams and representation attached to rho bar. So this is the application of this formalism of diagrams to local lineups, and that's all I want.